Well, good morning, everybody. It's great to be here, and thank you for that kind introduction, Mark. And it's wonderful to see so many people from the heap leach community out here today in Reno. So great to be here. Okay, so I'm going to start today with a quick safety moment, and it's very short. Speak up if you see something that doesn't look right. I often feel like I'm the guy hanging from the wall, but just be aware of everything around you and don't be afraid to speak up. Okay, well, this is going a little slower than I'd anticipated. So when I gave the keynote in Vancouver in 2013, I came up accidentally upon a story about Jack and Diane that I told. Were there any people in the audience that heard that? 1, 2, 3, 4, maybe 5, 6 people. Okay, so I'm going to do a recap of that story, but let me just first make a few qualifiers. No presentation here would be correct without a qualifier. This is a complete piece of fiction. None of the data presented is actual data, but it is aligned with experiences, and it's been developed to specifically illustrate a point or several points. Almost all of the names of characters, places, and companies in this story are completely fictional. So just want everybody to be clear about that. And anything resembling anybody within this presentation is completely coincidental. And I say that a little bit tongue-in-cheek. So back in 2013, we met this character, Jack, and he was working at the Cherokee Creek mine. It was just about an hour's drive outside of Pioneer Town in eastern Nevada. And he was one of many people who made that commute every day. It was a long commute. He had to wait quite a long time between slides. Okay, there's definitely something not right here. You told me to point it over there, so. Sorry? Okay, please advance one. So the flow sheet at Cherokee Creek was pretty straightforward, and many of you will recognize it as a standard gold heap leach flow sheet. They had a fairly large multi-lift heap in development. Next slide, please. And McCaffrey's and Associates did all of the test work on this ore prior to Jack getting there. And they did some great work at run-of-mine size in large diameter columns. And then they tested a number of different crush sizes to look at what the optimum would be. They did their economic analysis, and they decided to go with 80% minus 12 millimeters. And they were going to get a recovery of 78%. Next slide, please. So Jack, at the end of year 2, Jack had worked pretty hard. Throughput was on target. The crushing plant was running okay. The crush size was a little off, 16 millimeters versus 12, nothing major. He was doing pretty well. pH and cyanide concentration were good, and flow rates were pretty close to design. But the recovery was 60%, and this was problematic. Next slide. And of course, the general manager wasn't going to put up with this for very long. Jack was fired. And next slide. The want ad appeared in the papers, and Cherokee Creek were looking for somebody to run the process. Next slide. So we meet Diane. Now, Diane had been working at a couple of heap leach operations. She had a pretty reasonable understanding of heap leaching and what was going on. And she immediately got to work in trying to figure out what was happening. Next slide. Now, she knew that scaling up from column leach tests to a full commercial leach pad is quite tricky. And I'm not going to read any of these, but all of you will recognize these issues. There's a lot of issues that occur as you go from a column leach test result to a commercial leach pad. Next slide. And there are a range of different opinions on what type of scale-up factors you need to apply going from column leach tests to commercial. But most people are in agreement that there is some scale-up factor that is required. Now, next slide. Diane figured that really a realistic scale-up factor for a new operation like Cherokee Creek would probably be somewhere around 95%. So she'd expect to get to 95% of the recovery. Now, operations do approach 100%, typically after many years of operation. There are some that have hit close to 100% of column leach extractions fairly quickly, but it's really a bit of a stretch. So she prepared this graph that was what her extraction would be expected to be for lift 1 of the leach pad. Next slide. And of course, for many years, we've known as you add a lift onto a multi-lift leach pad, the grade of solution coming off drops because you've got dilution in the ore underneath. And of course, you've got delays just due to physical transfer of solution through the heap. Next slide. So Diane prepared another set of curves showing what she would expect to get out of each lift of the leach pad in terms of the timing. Next slide. She also did some work looking at how much inventory of metal, of gold and silver, would be held in solution. It's dissolved, but it's not come out of the bottom of the pad. And she spent quite a bit of time thinking about what the grade of that solution would be and came up with a methodology for how to calculate it and built that into an Excel spreadsheet. Next slide. And so when you actually take into account the metal in solution inventory in a multi-lift heap, you find that there are several % of recovery that are held locked up in solution in that heap until you eventually shut down a particular heap or move to another leach pad liner area. So you've got a number of things that are holding up gold and silver in solution. Next slide. And so she hired Mike Botts to prepare an Excel spreadsheet and develop these curves for each lift of the ore on the heap and built that into a pretty effective heap leach production model. Next slide. Now, she also knew that, of course, when she got on the job, the crusher plant was only delivering ore at 80% minus 16 millimeters. And she took a look at those recovery numbers, just the same data that Jack had, and she realized that that 4% recovery was actually quite a hit. Next slide. And she also thought about solution application. Now, Jack had been a little bit unlucky because they'd had a lot of rainfall, a lot of turbidity in solutions, and he'd lost a lot of drip emitters, and the solution coverage was not very good. They weren't leaching the side slopes very well. And she made a lot of big improvements to solution application and side slope leaching. Next slide. So finally, Diane did this reconciliation, and she took the original extraction indication of 78%. She applied the scale-up factor. She accounted for the metal in solution inventory in the heap and built that into a good Excel production model. She took into account the particle size differential of 4%, and then the poor solution coverage and lack of side slope leaching was another 4%. So that related back to their recovery of 60% that they were actually getting at the end of year 2. We go to the next slide. So she took steps immediately to get the crush size back on track, and that took a little bit of money to get the crushing plant up to speed. She implemented a clay control strategy. One of the problems they'd had was that they had regions of the heap that had higher clay than other regions, and she got a little bit out of that. She improved the solution application, and actually she at the end of doing that, she figured out that her scale-up factor was a little overly punitive, and she adjusted that to 96%. And her revised recovery projection for year 4 was 71%. Then she thought about it a bit more. Next slide, please. And she realized that if she accelerated the placement of liner, she could actually get inventory drawdown from the old pad. And if she did that, she was going to get that 6% of inventory off the old pad. She would start to build up inventory going forward. But she figured that really the overall apparent recovery at the end of year 4 was really going to be about 77%. So what did we learn from Jack and Diane part 1? First of all, we learned that Jack got fired for a 1% recovery delta. We learned that the test work done by McCaffrey's and Associates was dead right. They did a great job. We learned that the samples used for the test work were representative. We learned that you really need to apply a prudent scale-up factor to go from columns to commercial heaps. We learned that operational best practices pay off. Everybody in this room knows that. But Diane was systematic in her approach, and she was able to problem solve and figure out how to move forward at Cherokee Creek. The other thing that I presented back in 2013 was just this set of expectations for what a production model, an Excel-based production model, should be able to accomplish in terms of variability. And, you know, with heaps, as several people have commented this last couple of days, it's not a mill. You don't have instant feedback within 24 hours on the recovery. And our ability to forecast is impaired just because of the inherent variability of many of the things that happen in a heap leach operation. Next slide. So Jack had a little bit of unplanned recreational time, but then he got a new job. So let's move on to part 2 and see what happens. So Jack joined the Marsupial Mining Company in Western Australia. It was an operation called the Big Dingo Mine, and it was located about 100 kilometers outside of Kalgoorlie, not to be confused with the other town that's a fairly similar name. It was a medium-sized copper operation, processing 40,000 tons per day of ore containing 0.6% copper. Let's, next slide. The ore was crushed to 80%, passing 12.5 millimeters. It was agglomerated with sulfuric acid and leached on a lined heap leach pad. Copper is recovered from the leach solution using conventional solvent extraction and electrowinning. The expected metallurgical recovery was 76%. The annual copper production was budgeted at about 66,500 tons per day. Now, like all secondary copper sulfide heap leach projects, it was designed with air injection into the heap. And in this case, the air injection piping was to be installed every 4th lift to provide air for up to 4 cycles of leaching. And the leach pad was designed to an ultimate height of 100 meters with a total capacity of 146 million tons. So a big heap. Jack had arrived at the mine just as the crushers were being commissioned. The mine engineer had contacted him prior to arrival to get his input on the metallurgical recoveries and how to incorporate these into the mine production plan. The metallurgical test work had been performed at a lab in Perth, funnily enough, owned and operated as a satellite facility by McCaffrey and Associates. Now, he had a lot of faith in McCaffrey's test work based on his prior experience at the Cherokee Creek mine in Nevada. Although he'd been fired from Cherokee Creek, he'd learned a lot and he knew he could trust the results of the McCaffrey's test work. He was pretty happy with what he saw from the test work results. Now, the copper was mainly present as chalcocite with minor amounts of oxide copper and primary copper sulfides. Can anybody see what's coming? The average of the column leach test extractions was 79% after 180 days of leaching. Now, he realized that the corporate metallurgist had insisted on applying a 96% scale-up factor to these recoveries, and he was pretty happy about this because that was one of the tough lessons he'd learned at Cherokee Creek. Now, acid consumptions were moderate, ranging from 4 to 8 kilograms a ton and averaging about 6 kilograms a ton. Now, Jack had identified three main ore types when he reviewed the test work. Ore type A was dominantly chalcocite. Ore type B was 80% chalcocite and 20% chalcopyrite. And ore type C was 80% chalcocite and 20% oxide. When he back calculated the column leach extractions for each, he got 82% for ore type A, 72% for ore type B, and 84% for ore type C. And the proportions of each ore type were 60% ore type A, 30% B, and 10% C. You don't have to remember all these numbers. We're going to come back to them a little bit later. The crushing plant started up just fine, and the heap construction proceeded as planned. Next slide, please. They were building 8-meter lifts on the heap, stacking in retreat mode. The agglomerates looked good, and the stacked ore density was 1.7 tons per cubic meter. These are big tons, by the way, Manly metric tons. The first lift of ore was leaching rather well. The PLS grades were hitting the target of about 1.5 grams per liter. However, as they started the second lift, they ran into some problems. Firstly, the dozer tracks on the stacker started to sink into the ore. Jack didn't worry too much about this, at least not at first. Then he realized they would need to shut off solution much earlier before bringing the stacker back on top of the leached ore. Then they began to encounter solution ponding on top of the second lift. Next slide, please. They had to shut off several cells of the heap to avoid runoff down the sides of the heap. Now, Jack was puzzled. They were applying solution at the industry standard application rate of 0.004 GPM per square foot. Now, I've got in my notes written here 10 liters per hour per square meter. Jack had to figure out how to convert from these lovely imperial units to metric units. So from now on, you're all going to have to eat it because we're going to talk about metric units. So 10 liters per hour per square meter is 0.004. They were using drip emitters on 1 meter by 1 meter centers. And to counteract the need to shut off flows to several cells, he'd increased the raffinate flow to areas of the heap that were not ponding to 12 liters per hour per square meter. Much to Jack's frustration, the proportion of the heap surface that had ponding actually seemed to increase. As they approached year end, Jack started to get really concerned. PLS flows had dropped, and so had the solution grades. Instead of producing 5,500 tons per month of cathode copper, they were only producing 4,500 tons per month. And the general manager was getting on his case. He had a depressing sense of deja vu, but he was not going to let this problem get away from him again. Also, and this was very worrying, Mark, where are you? A few springs had started to appear between the first and the second lifts of the heap. Next slide. He decided to give his good friend Diane a call. She was still at Cherokee Creek, and the heap leach operation there was running well. Hi, Diane. Jack here. How are you doing? Well, great, thanks. Good to hear from you. Jack explained his predicament. Diane was concerned when he told her about the springs that had appeared on the sides of the heap. How much clay do you have in the ore, she asked. Not sure, said Jack, but let me go and talk to the geos and I'll get back to you. Sure, we have some clay in the ore, said Bob, the chief geologist, responding to Jack's question. Our guys put it on the logs. Well, can we take a look at some of the logs? Sure, said Bob. So they wandered over to the core shed and Bob pulled out paperwork. Well, this one says there's clay intermittently all the way down the hole. Oh, and this one, and this one. Jack asked to look at some of the drill core. So they pulled out boxes of core. They pulled boxes of drill core for a few holes, particularly the ones with significant clay logged. We got pretty poor core recovery from a lot of these holes, said Bob. You're not kidding, said Jack. Then he asked, how do your guys know what is clay? Oh, they know it when they see it, said Bob. Jack thought about this for a while. Sure looks like we have a lot of clay in fines on the leach pad, and it sure looks like we have clay in the drill core, or at least some remnants of clay zones. What if the clay is getting washed out of the drill core? He decided to take another look at the McCaffrey's test work results. There was very little evidence of any clay content or permeability problems. In fact, they'd run load permeability tests on composite samples of the three main ore types, and everything had looked pretty good. They hadn't given it another thought. Also, he was bothered by Bob's comment, "They know it when they see it." Next slide, please. He did a bit of research on clays, and he found out that clay is any particle that is less than 4 microns. He couldn't find any reference that said specifically what mineral the clay was. So the geologists were analyzing clay as anything less than 4 microns. And he did a lot of reading on this. Surely the different types of clay have different effects on the leach pad. How can the geologists identify and quantify the different types, he thought, with this kind of information? So he prepared the following classification. Next slide, please. So he divided clays from his research into these 4 categories. And when I say clays, he divided particles that are less than 4 microns into these 4 categories. Swelling clay minerals, and you can see them listed here, which are mainly the smectites, but also vermiculite and mixed layer illites. Then he got into the non or low swelling clays, which include pyrophyllite, talc, kaolinite, illite, and chlorite. And pyrophyllite and talc are kind of interesting because they do have some swelling properties, or can have some swelling properties. Then he said there are clay forming minerals, and he put three minerals into that category. And then finally, he got to non-clay fines. These are fine particles produced in blasting or crushing that are fines, but they're not necessarily clay. So he was pretty pleased with this classification. And he also thought, maybe, it's all very well to be classifying clay as any particle less than 4 microns, but shouldn't it be less than 4 microns in situ? Jack called the mine engineer and asked if he could go with him to take a look at the blast hole drilling in the pit. They went down into the pit at noon. It was midsummer down under, and it was hotter than Hades. Jack took a close look at drill cuttings from a few of the holes. He put a few drops from his precious water bottle onto some of the cuttings from one of the holes and pulped them up in his hand. They merged into a lump of malleable modeling clay that retained its shape in his hand. Now this is clay, he thought. Jack decided to call Diane again. Well, we definitely have clay in our ore. We can see it in the blast hole cuttings. We just don't know how much or what it means. Now, Diane had run into this before. You can analyze blast hole samples for clay minerals. There's a method called cation exchange capacity, which will give you an accurate quantitative measurement of swelling clay and non-swelling clay minerals present. When you combine this with XRD measurements, you get a pretty good estimate of the clay and fines forming minerals. Geez, that sounds pretty complicated and expensive, retorted Jack. True, said Diane, but you can also use a near-infrared instrument to estimate swelling clay and non-swelling clay content, as long as it's calibrated against quantitative cation exchange capacity, or CEC, and XRD measurements on a representative set of samples from the deposit. She carried on. The NIR instrument is inexpensive to buy. It performs the analysis very quickly, and it is simple to run. Any lab tech can be trained to run it. Next slide. You can see here, this is her calibration she showed him over Zoom, where she showed how muscovite, biotite, kaolinite, swelling clay, and chlorite were calibrated using XRD results. The one on the right there, which is swelling clay, is calibrated using cation exchange capacity. So you can calibrate the swelling clay to be read on the near-infrared instrument. She went on. Actually, once you've done the calibration, it's very cheap to run NIR analyses at the mine site. Costs us less than $5 a sample. But why is it so important to have accurate clay analysis on site, asked Jack. Diane knew Jack well by now, and she knew that he was skeptical of doing this type of work. We had a similar issue at Cherokee Creek after you left, she said, and we found we had swelling clay and non-swelling clay. The swelling clay is a killer because it can swell up to 20 times its original volume on contact with water and can completely fill pores and voids in the heap in the worst case. Okay, 20 times is a bit extreme, but even swelling just 2 to 3 times is a problem. Look, if you have 5% by weight of swelling clay in the ore, it can swell to take up 12 to 18% by volume in the heap. That's a lot of pore volume. Non-swelling clays can also be problematic because they can migrate and aggregate in certain zones within the heap. Actually, the adverse effect on permeability gets worse the higher the solution application rate. What did you say? Said Jack, cutting her off in mid-sentence. Yeah, clay migration, segregation, and compaction gets worse the higher the flow rate, exacerbating permeability issues. Jack's light bulb went on. Yes, continued Diane, we found that applying a lower solution application rate in the early portion of the leach cycle, followed by a ramp up to the target application rate, reduced ponding significantly and allowed us to keep all cells running on the heap. And I think most people in this room understand this issue. Jack was a little bit slower. Wow, said Jack. Diane was on a roll now. Actually, we had thought that we would have to implement an ore control criterion for clay content and send material with high clay to the waste stockpile, even though it was ore grade material. Luckily, we didn't have to do that because the solution application control took care of the problem. After more discussion, Jack thanked Diane and hung up the phone. How are we doing on time? We're fine? So, sorry, Jack just hung up the phone, right, with Diane? Next slide. He immediately issued instructions to the heap leach operators to run at a reduced solution application rate of 4 liters per hour per square meter for the first 14 days of the cycle. That allowed him to wet up all the clay material, the clay minerals slowly. And then he would ramp up to a target application rate of 8 liters per hour per square meter, a little bit lower than the original design. Gradually, he was able to reduce the number of cells that had ponding and increase the area under leach. And the PLS flow rate kind of started to increase a little bit as the situation improved on the pad. Now, while he was coming up with this plan, he thought back to the small amount of load permeability testing that had been done earlier on the project, none of which had highlighted any specific problems. He decided to get some fresh representative samples of each of the 3 ore types from the infill drilling that had been done by the geologists since startup, and he submitted these for updated load permeability testing. Now, since his meeting with Bob had been thinking about this problem too, and the geologists had modified the core drilling procedure to use an additive that significantly improved the core recovery. Ah, bingo. In addition, he sent out a suite of 100 blast hole and drill core samples covering all the ore types, together with the 3 composite ore type samples for CEC, XRD, and NIR analysis to determine swelling clay and non-swelling clay content. A month later, he got the results of the load permeability testing, and he got these in the form of 3 sets of graphs that I'm going to show you now, and then we'll switch back among the 3. So the first graph he got back was the next slide. Sorry, if we could go back one. Just before I leave that, he also hired a geotechnical engineer to come in and look at the portions of the heap that had springs between the first and second and third lifts, and they implemented some mitigation drainage. So that's an important point. Next slide. These are the results of the saturated hydraulic conductivity on the y-axis with simulated heap height on the x-axis up to 100 meters of heap height. The top graph, the darker blue, is ore type A, which if all of you, I'm sure, remember, that's 100% chalcocite ore. The next one down, the yellow line, is ore type B, and the third one, the light blue, is ore type C. The green line is the original target solution application rate of 10 liters per hour per square meter. The red line is what a couple of consultants had told Jack was the required saturated hydraulic permeability, which was 100 times the planned solution application rate. And Jack knew that there were a range of opinions on what safety margin was needed. But nonetheless, he wanted to look at the data and look at it at face value. And he could see that ore type A didn't really have any hydraulic problem up to 100 meters. If we go to the next slide, this shows the degree of saturation on the y-axis in percent so this is the proportion of the voids that are filled with liquid, and the simulated heap height again on the x-axis. And you can see the dark blue line on the bottom shows the degree of saturation in the ore type A going from 40% up to about 70%. Pretty reasonable. And then the next slide, this shows the air conductivity in centimeters per second against simulated heap height. And the red line in this case is the planned air injection rate. So you can see here for ore type A that just over 50 meters, the ore type A is not able to be air permeable at the rate planned. So now if we go back to the first graph, this one, you can see ore type B, the threshold of 100 times the application rate, ore type B passes that at about 60 meters. By 100 meters, it is around somewhere a little over 10 times the application rate. And that was a bit of a flag for Jack. He was not terribly excited about that. But alarmingly, ore type C gave a real problem. This was at 80 meters. He could not get conductivity at the planned application rate. So he had a big problem with ore type C. Next slide. And as you would expect, the degree of saturation exceeded 85% at about 45 meters. So that's a massive flag for ore type C. And then the third slide shows that the air conductivity was impaired at about 10 meters for ore type C and 27 meters for ore type B. So air permeability is a big problem. When you're leaching chalcocite, air injection and air flow is critical. Next slide. So a week after he got the load permeability results back, he got the clay analysis results back. And he plotted a bell curve of results for swelling clay, pyrophyllite, kaolinite, chlorite, and muscovite. Now, based on his XRD analyses, these were the main contributors to the fines content in the ore. He realized that the swelling clay content was bimodal, with about 6% of the blast hole samples containing 10%, more than 10% of the swelling clay content. And these samples also contained elevated pyrophyllite, kaolinite. He realized that a small percentage of the samples contained the highly elevated swelling clay, pyrophyllite, and kaolinite. So he plotted these up on their own in the next graph. And you can see here, the swelling clay is the blue curve, the pyrophyllite is the orange or brown curve, the kaolinite is the gray line. And when he summed those percentages, he got the green curve, and it showed a bimodal distribution. And 10% of the samples contained over 20% of the swelling clay plus pyrophyllite plus kaolinite. So with this information, he put together the following table. So he plotted tabulated the three ore types, their weight percentages, and then he did a little bit of a mass balance on the swelling clay, pyrophyllite, and kaolinite. And obviously, ore type C was quite stark in its SC plus P plus K content compared to the other two ore types. So we wanted to superimpose this on the saturated hydraulic conductivity curves. Next slide. And so, not surprisingly, this is what he got. The poorly performing ore type C had an SC plus P plus K of greater than 20%, whereas the other two ore types were significantly lower. And he thought he might be able to do something with this. Next slide. So he decided to implement a new ore control strategy. And he implemented measurement of the SC plus P plus K in the blast hole samples by NIR. So he used his new Bruker matrix NIR analyzer, and he set a target to the mine planners of the crusher feed containing less than or equal to 12% SC plus P plus K. And material that couldn't be blended would be stockpiled for future blending to meet the target or sent to waste. But he also implemented a threshold of 15% for swelling clay. Anything above that would be sent to waste because it would be very difficult to blend to meet the target. This was a very small amount of the resource as well. Also, after talking with the geos and the mine planners, he knew the proportion of ore type C was going to decline in the future as they pushed further into the deposit. So he thought this approach made sense. Next slide, please. So what did he do? So for hydraulic conductivity, he remained concerned that he might have problems at heap heights above 60 meters. An engineering company that he hired suggested that he look at installing interlift liners in the heap between lifts 5 and 6. Didn't take him long to figure out that that wouldn't work for a secondary copper sulfide leach when the residual copper recovery from buried lifts is so crucial to overall recovery. Also, no one within the engineering company could tell him how he would recover the copper in solution inventory beneath the liner. So that was a no-go. He wondered just how much it would cost to add more liner and reduce the ultimate heap height to 60 meters. And he asked the engineering company to run an economic analysis. Now, it turned out that it was NPV neutral to add more liner because the inventory drawdown paid for the cost of liner installation. The only drawback was space and the permitting of the new liner. They had space, but the environmental manager told him that it would take 18 months to permit the new liner and then another 6 months to install that liner. Now, luckily for Jack, he discovered this problem at the end of year 2 with only 4 lifts on the pad. And he figured he could go up to 8 lifts on the existing pad, which would buy him another 2 years. He still had another problem. The hydrodynamic performance of ore type A was good, but ore type B still showed the potential for impairment at 60 meters. So, and the airflow at 30 meters. The new ore control parameter alone would not solve that issue. So he decided he better start installing air injection piping every 3rd lift instead of every 4th lift. This would only increase the operating cost by a fractional amount, about 1 cent a ton. And this was a good insurance policy. He would still inject the same amount of air into the leach pad. All of these modifications were pretty workable. And Jack kind of began to think that maybe his luck had changed. Something to do, or was it something to do with what he'd learned at Cherokee Creek over the years? And that made him think about Diane. Better give her a call, he thought. Hi, Diane, Jack here. How are you doing? Well, great, Jack. I was just wondering how you were getting on with your clay problem. And so he talked her through everything he'd learned over the past few months, what he'd done to identify the problem and what he was planning to do about it. There were a lot of silent pauses. Rather than Diane's previous habit of biting her lip to buy time to think about how to respond to Jack's stubbornness, those silences were attributable to Diane's furious note-taking during the call. Wow, Jack, I'm hearing a lot of good ideas that I can use and implement at Cherokee Creek. You don't mind if I steal with pride, do you? Of course not, said Jack, quietly surprised at Diane's enthusiasm. Next slide. 3 months after implementing the new ore control strategy, he could see a big difference in heat performance. Ponding was reduced significantly. Sure, he still had to deal with a few historic seats between lifts 1 and 2 and 2 and 3, but these issues could be managed as long as it wasn't going to happen through all 12 lifts of the heap. Also, he brought in the geotech engineer to come up with a plan to de-risk the side of the heap in the areas where the seeps occurred, and they'd installed some mitigation drainage in the heap to take care of this and prevent washouts. The surface area of the heap under active leach began to improve, and PLS flows went back to design levels. Sampling of heap feed material showed that the working moisture in the heap had returned closer to design level. Now, this was good for inventory holdup in the heap, he thought to himself. 6 months after implementation of the new strategy, copper production levels were approaching design. His Excel model had started to perform close to expectations, which was a huge relief. They'd immediately started the permitting process for the new leach pad area. The permitting was on track, and the liner construction package was out to bid. Next slide. So the general manager was pleased with how things were going, and he said that to Jack during his performance review. What a turnaround, huh? But Jack's mind was already wandering elsewhere. They had a primary copper sulfide deposit underlying the secondary sulfide deposit at Big Dingo, and he needed to figure out what to do with it. As soon as he got out of the meeting, he called Diane. Hey, Diane, it's Jack. Do you know anything about chalcopyrite leaching? Funny you should ask that, said Diane. Actually, I was just doing a bit of research on that for a new exploration project we have in Chile. Oh, great, said Jack. Maybe we can get together when I come up to the States for the next Heap Leach conference to discuss. Sure, said Diane. Look forward to seeing you there. Jack hung up the phone. Slide. Next slide. Well, life sure was good in Calgary, thought Jack. Thank you.
Thank you, John. That was an excellent part two. I very much enjoyed that. And honestly, I didn't know exactly what to expect because I didn't get to see part one. So that was fantastic. And in fact, we're a few minutes ahead of schedule, which is quite nice. So we've got a time for break now. The exhibit hall, of course, is open. There'll be refreshments next door. We reconvene at 10:15 sharp, and we'll have the two parallel sessions, one here and one in the other room, same rooms as yesterday. And it looks a lot to me like Dan has something to tell me, which normally means I did something wrong.
You guys can find your way up to our office at 15 minutes from here. But also, if anybody wants to meet here and meet the ride up there, let's plan on giving otherwise, you're welcome to stop up anytime you get tomorrow.
Was everybody able to hear that? If not, I can repeat. Okay, excellent. Yes, thank you very much. I've had the pleasure of being in Dan's facility multiple times. We've worked on a number of projects. It's very much worth the 15-minute drive north, as is Gene McKellen's facility a bit closer in town. So if you've got time to do that, I highly recommend it. Okay, thank you. Break time.